So I'm going to describe for you an idea which is relatively new for our group and a little bit raw, which is this idea that's powering the Snorkel system, and is really, we think, a new way to program some of these machine learning and AI systems. But to understand sort of how we got there and why we're excited about this idea, I thought I'd give you a little bit of history about sort of what Deep Dive has been doing and how we came at this problem. So we worked on these problems called dark data problems for a couple of years. So data that's not dark or clean are these kinds of data that are in structured, nice, clean sources. Think a SQL database, an Excel spreadsheet, something that a machine precisely and cleanly understands. Now, as Feifei mentioned, most of the data that's created right now, the overwhelming majority, is not in that clean, nice, structured form that machines really know how to operate on. Instead, it's generated in things like medical images or videos, scientific articles, and government reports. And so a couple years back, we started looking at this data growth and saying, we have to figure out how to take all that data that's, below the surface and translate it into that nice, clean, structured format so that it can be used throughout a host of different applications. And indeed, we built this system called Deep Dive, which was one of the first dark data systems that would take all of that information in and try and translate it to that nice, clean, structured, precise format. Now, the way this is done by and large in industry, even today, is that people sit down and read that information manually. They pay contractors or someone to read it, and they enter that information in manually into that clean, precise database. And in about 2014, we had a really exciting result that showed that Deep Dive for some of these real end-to-end applications could take the same input as the people and produce the same output that they were producing, except with higher quality. This was sort of an inflection point where we could start to think about replacing people doing this task with machines. And indeed, what we did over the next couple of years is try and take this and apply it to a bunch of different domains, not just scientific domains, intelligence and defense domains, drug repurposing. We have a bunch of stuff on lung cancer prognosis in collaboration with the hospital. And even societal kinds of impact. For example, we had this project with DARPA Memex that was actually reading ads all over the United States to look for examples of people that were trafficked, look for human trafficking. And this is now actively used to make arrests all over the US and decide where to launch investigations. So we're really excited about this, and as Steve mentioned, we spun out a company called Lattice that was meant to service a bunch of these contracts and a bunch of other folks now. But as we built these things, we realized that they were really very difficult to construct. And somehow that's natural. If you're going to construct things that are better than people, you expect to pay some engineering costs going in. But what was kind of depressing to us is we saw that somewhat routine cases that should be really, really easy, were in fact really quite challenging to use machine learning for. And so we started on this quest to try and make radically easier to use machine learning systems for a smaller class of problems. Problems that we saw coming up again and again where people would come and say, we don't need the full sort of deep dive stack. We just have a question that requires a little bit of natural language processing, a little bit of object detection, something simple. And as we started building this and working with a bunch of our fellow companies and sort of scientists around campus, we started to realize something that really troubled me, which is that these machine learning systems should be dramatically easier to program, but in fact, right now, they're dramatically harder. And the reason they should be easier is that machine learning systems should be able to take, in this next generation of systems, dramatically less precise input. Instead of today's programs that must be tediously specified line by line, it seems like these underlying systems should be able to cope with that ambiguity and thereby open a huge class of people who can't program these systems to be able to program them. So we wanted to hold our feet to the fire, as we often do at Stanford, and luckily we're in the center of the tech universe, which is great. So people were coming by, and we have these office hours, and we have them basically try and program with these new paradigms and see, can they, having never seen this system, get world-class quality in a couple of hours? So things that used to take days or months, can we have them do it in a couple of hours? And this is, of course, a stretch goal. This is something that's our vision on the horizon. But the shocking thing is, even though this prototype's only been around for a little under a year and only been usable for about 6 months, it actually works. And sometimes, for some limited cases, we can actually do things that used to require machine learning PhDs, now with folks who don't really know all that much about machine learning. They're domain experts or subject matter experts. Everything I'm going to talk about here is on a website called snorkel.stanford.edu. There are a bunch of blog posts that my students have written. Here's a selection of those students, not all of them who actually work on this. They did all the real work, but you can read about their individual contributions to this project that's really exciting and just getting started. Okay. Now, as Feifei mentioned, sort of the world changed, and for computer vision, it changed when the sort of ImageNet challenge came along, and then all of a sudden deep learning sort of came online. The problem that deep learning solves underneath the cover in sort of vision and also in natural language processing and a host of different areas is this narrow small bore question around what's called feature engineering. That is, you take a bunch of that unlabeled sort of dark data and you have to learn the representation that the machine is going to learn on. And what we realized over the last couple of years is that that process, that mapping step, is really difficult even for the best PhDs. So deep learning has caught on for a host of different tasks, and the progress has been so rapid that in areas like natural language processing, there are sort of de facto standard deep learning models that now give you pretty close to state-of-the-art results. Now, the dirty little secret that's under deep learning is actually something Fei-Fei alluded to as well, which is that you need pretty large, what are called labeled training sets. You need huge numbers of examples to get state-of-the-art accuracy on a lot of these tasks. And while Fei-Fei is constructing ImageNet and Visual Genome, those are great benchmarks to advance the field. But if you're someone who wants to build an application in 4 hours, you probably can't spend a couple of years labeling data. So what we realized when we were interacting with people is that this step of creating labeled data was the real bottleneck. And we wanted to figure out how could we attack it. And this was broader than dark data kinds of problems. It's really a fundamental problem throughout all the areas where we're deploying machine learning today. And so this is glibly summarized by this slide here, that it used to be that data was the limiting reagent. If you didn't have enough data, you couldn't sort of play in the game. But now it seems for a bunch of these different high-end tasks, if you don't have enough training data, you also can't build the state-of-the-art machine learning models. So all that great progress around deep learning will kind of leave you behind if you're not able to construct those data sets. Now, to be clear, that's a lot of progress, that we've moved the barrier from constructing models to labeling data. That's a substantially lower-end task than actually writing this. But it still seems like we're not quite reaching the promise of having these really intelligent systems. So at some level, saying that you need a lot of training data to be able to build good models is a lot like saying, if you want to be rich, you should have a lot of money. It doesn't, it's technically true, but it's not really operational. Like, what could you possibly do to create training data? If you're sort of a traditional statistics or machine learning person, training data shows up from God herself, in this case, often Fei-Fei's lab. It shows up, you label it by hand, and you can't figure out sort of where it came from. Now, in any reasonable kind of deployment, you actually create training data. You actually do it by a process, and that process is imperfect. Even the best Stanford PhD makes errors when they label. But more often, you want to use sloppier, less precise methods to label data and still learn from those. And if we can do that, we can dramatically lower the cost of building this next generation of models. And so this is the key idea that we've been pushing for the last year or so and realizing that it works in a host of different domains, is that we can model the process by which training data is created, by which people, by which systems. We can understand the conditions under which that data is noisy or imprecise, when it should be trusted and when it can't be trusted. For experts, what I'm talking about is we're looking at generative models, and we're able to provide new situations under which generative models can learn without any labeled data whatsoever. And that's what our series of theoretical papers are about. Now, we care about sort of theory, and we do it, maybe because of a misspent youth or poor PhD upbringing. But what we actually care about is, does it change the way people program? And so this Snorkel prototype, what it's all about is putting it in people's hands and seeing if the theory, which makes some statistical assumptions, is actually valid in the real world. And so I'll share with you, as I said, it's very raw, it's new, and it's ongoing. This is something we're quite interested in. So let me explain to you concretely why this comes up, and I'll give you an example from sort of our dark data, sort of lightweight text extraction kinds of things. And just to be concrete about what the steps are when you build this and why we think this is the place to spend our bullets and our effort to try and make these systems dramatically easier to use. Okay? So if you want to build one of these systems that used to take months or years, and you want to answer a question in hours to days, what's holding you back? What are the steps that you have to do, and where does your time actually go? So let's take an example, which is actually a real example, that comes from folks who want to label which chemicals cause which diseases. Okay? I don't expect you to read any of this text. It's far too small. I'm just going to use it as a schematic. Okay? So how does it actually work? Okay? So the task that you typically have in this scenario is you've somehow defined some candidates. You've figured out which chemicals and which diseases are in your text. We'll come back to that in a moment. And your goal is to try and figure out, from that information, how you can populate a large data set. Okay, figure out which chemicals cause which diseases, right? So how does this work right now with machine learning? Well, first there's this phase called candidate extraction. You say what are the possible relationships that are there, okay? This, by and large, is actually a relatively easy step, and there are basically libraries that will take care of this for you. You can be extremely permissive here, and that's where machine learning buys you a big edge. You don't have to get every disease right. You just have to have, say, 20% of the diseases correct, and you'll figure out which ones are accurate. You then create a training set, which means you label some of these different pairs. Then you do a process called feature engineering in sort of classical systems. Which words indicate that there's a relationship between these two mentions, the verbs that are there, the prepositions, all the things that statistically indicate that two words are related. And then you do a process called learning and inference. Okay? Now, the point is today you have to do most of this pipeline, but actually each one of these steps is not so challenging. In fact, candidate generation, we have a series of papers, as do other people, showing that you can basically take the simplest candidate generator you can imagine, and the machine learning is so powerful that it will be able to pick out that needle in the haystack of which candidates are relevant. So you can continually relax this, and operationally, it's almost never a bottleneck. Learning and inference used to be a bottleneck, but we spent the last, sort of collectively in computer science, scaling up learning and inference. And now you can get commodity things that you can download from the internet that will run on, petaflop scale machines pretty reliably. It's kind of insane. And so lots of people, and myself included, worked on sort of the algorithms to scale up inference and learning. But for someone who has a problem in front of them, it's doubtful that their needs outstrip even what's sort of readily available to download or run on any of the public clouds. So there are these two boxes still here, feature engineering and sort of training set creation. And it used to be that feature engineering was the long pole in the tent. That's where you spent all your time. And you spend all your different time there. Now, there was a little quote on Twitter, which is the source of all truth, that was actually from Chris Manning's keynote, to tell you why feature engineering for natural language processing is kind of going away. So don't worry if you don't know all the buzzwords. This field, deep learning, is replete with insane buzzwords. It doesn't matter. You don't have to worry about what a bidirectional LSTM is. But the point that you can glean from this in his keynote is that to a first approximation, these models have really become a commodity. There's literally one model you download for most of the NLP tasks that you want to run, and that's it. No more tweaking and tuning with them. So feature engineering in its current form is dying, except for the high-end models that you need. And we hope in 5 or 6 years it will completely die. So what's the gating reagent? It's the training set. Actually creating the training set about your particular task. And the worst thing is that to be able to do this requires absolutely massive training sets. It's not enough to have sort of small, little training sets to do this, because you have to learn the target, that is what you're after, and also be able to learn the representation as well. And that requires a huge amount of training set. Okay? And so this is the big central idea, the crazy idea. By modeling the noise in the training set creation process, we can, instead of using high-quality training data sets, we can use far lower quality training data sets. And that asymmetry in cost is substantial. Generating a manually curated, nearly 100% accuracy training set is extremely expensive. It requires annotators that are checking one another. Generating one that's 70 or 80% accurate is actually pretty easy and sloppy. And we hope that this asymmetry allows us to be dramatically, dramatically faster at building these kinds of training sets. So just to explain sort of sensibly how this works, when you look at things like Snorkel and the prototype, you can go and play with it and download it. I'll go through it relatively quickly. Basically what happens is you load in a bunch of unlabeled data. You write these things heuristically called labeling functions. I'll illustrate one schematically on the next slide. And then you choose a discriminative model, something like an LSTM that we just talked about. And what's going on underneath the covers is that Snorkel is basically taking all that information and it's learning the noise and accuracy and conditioning under each of those heuristics that you've given it, and does all of this without any reference to a hand-labeled data set anywhere. Now, if you have hand-labeled data, that's great, but that's not really the research or the art component. The research that pushes the envelope is to try and say, what can we do if we never have hand-labeled data? How far can we go? And that's what we're doing in this project. So given time constraints, I won't run through exactly how this works. I will show you one example of how a labeling function works. Here's an example, traditional thing. If chemical A is found to cause disease B, and it's in our database, we say it's true. Okay? We're looking for causes. But that can be false, this rule. A and B can occur in a sentence and also be false. So we can use these low-quality, cheap rules, and many, many, many of them, to be able to learn the accuracy of the training set nearly automatically. And this captures a huge amount of other kinds of weak supervision, crowdsourcing, weak classifier, domain heuristics, and so on. Okay. Now, what we really care about is that it works. And this is one of those 4-hour hackathons. And these are people who were bio experts who came in and wrote labeling functions that we taught them how to do in about 4 hours. For comparison's sake, it took them about 4 hours to install Python. So these are not machine learning PhDs. And they were able to use it. And we were really excited. Now, it doesn't work. It hasn't worked in every one of these trials. It's research. It fails all the time. It's not a product. But it is actually, crazily enough, in use throughout campus, and this slide is already out of date. It has hundreds of users, and we just, as I said, had a usable prototype in the last 6 months. And this is the big bet. We have more examples of this. I'm happy to talk about it or talk to my students offline. That this will allow us to fundamentally change the notion of programming. Rather than tediously specifying programs one step at a time, this is a new paradigm where you're programming very noisily, very lossily, and potentially we can build these applications dramatically cheaper. And what's amazing is you would think that there would be a trade-off to lose quality. But what we've seen over the last year is that it's simply not true. You can build higher quality applications this way because your cycle of iteration is indeed so much faster. So the last thing I wanted to mention before I conclude is that this is just one part of a larger project that's going on, this thing called Dawn. It has one of the ugliest logos I've ever seen in my life, which is right there. This logo was created by Peter Bayless. Peter makes up for his lack of ability to create good logos with an unbridled enthusiasm, so we're really excited that Peter's here and new, so please go and chat with him today. Kunle is also involved, and so is Matej Zaharia. This is basically looking at the problems in machine learning that go from how do we change how they program, which is the kind of side that I work on and a little bit of the theory, all the way down to how do we run these efficiently on hardware and deploy machine learning systems that are out there in the world. And it's a new project called Dawn. Please check it out and talk to those folks. So to conclude, I just wanted to share with you a little bit that this problem, this narrow, seemingly niche problem of translating dark data to structured data, we think has societal scale impact. Things like human trafficking, the best diagnosis for cancers, these are all coming out of, in my view, this way of taking access of all the information that's already out there and putting it into a usable form. What's bothered me incessantly and why we started on this work is that machine learning techniques have the ability to make it radically easier to program, but yet they seem to require an increasingly narrower and narrower set of skills. And this has to change. We have to make this technology available to a much broader audience, and that's what we're going to do. And the last bit, as I said, is this prototype Snorkel, which is very rough, and I still don't understand why so many people use it, but we're really happy that they do. It's kind of awful, to be honest with you, in its current state, but people use it and give us feedback, and so if you use it and give us feedback, we'd be really excited about that. Thanks so much for your time and attention.
Thanks, Chris. That was great. We have time for a couple of questions.
Thank you. I'm Kazuhiro from NEC. Thank you for introducing your decent work. And first, I want to say, in the very beginning slides, I feel very sad because our research paper are categorized into the dark data. So, but when you show you said the crazy idea, I suddenly think that maybe in your technique, if we use your technique to just change our dark data scientific paper into the light surface, so do you think is that possible to use your technique to support this?
That's a great question. So one of the first applications, which I went over a little bit too quickly, was that we were taking actually scientific articles in sort of geoscience and biology and transforming them into that clean, structured, precise format. In fact, Deep Dive still runs underneath a number of collaborations. PaleoDB is one. There are a couple of medical collaborations, and in the FDA, I think it's running as well now, where they're able to actually do exactly that task. And that's what motivated us at first. All this great scientific literature that's sitting out there and sort of unusable for a bunch of downstream analysis is just too difficult and expensive to use. So that's something we've done quite a bit on the research side, and we hope that Snorkel will continue to power some of those applications. So we're of one mind. It'd be great to get more of that data into the hands of people who can use it.
Great. Please join me in thanking Chris Ray.